Good morning, class. All right, today we are moving on. We are doing speed and velocity. So, hypothetical situation. I'm standing at the front of the room with my racquetball, which if you've not seen yet, you will see soon. And I throw this racquetball to you. So currently, we can explain that motion. We could say that racquetball has a displacement of 2.5 meters in the positive direction. Beautiful, we can explain that motion. Is that all you would need to know? So, what if I threw that racquetball at 5 miles per hour? What about 20 miles per hour? What if I threw it at 85 miles per hour at you sitting in the front row? So, would it be nice to know not only the displacement, its change in position, but how fast or the time over which that change in position occurred? Yes, that would be helpful to know, right? So that's what we're talking about today. And just like distance and displacement, there are scalars and vectors here. We'll be dropping the scalars soon, more for the effect of they're not as useful, so we won't use them much. But we'll keep them going today just so you can see the difference between them. So our scalar is going to be our speed. So speed is the distance traveled in a given time. So it is a scalar value. It has no direction associated with it. This is why you have a speedometer in your car. It captures your speed because it just looks at the distance you're traveling over time. It doesn't care what direction you're going. You can go 65 miles per hour north or south or east or west, and your speedometer is going to measure that the same because speed does not care about direction. So we have our vector value speed, lowercase s. We will almost never use this formula here. Because if you're going to get speed, distance divided by time, why wouldn't you just go one step further and get the displacement? The velocity. Velocity is a much more descriptive word or term in physics because it adds your direction in. It becomes a vector. So speed will be here. We're not getting rid of it, but it's certainly used less in physics. Usually we're talking velocity because we want to know not only its distance traveled over time, but its direction. So in velocity, we're going to do displacement divided by time. So since displacement is a vector value, that means velocity has to be a vector value. So velocity is just the change in position in a given time. It's your displacement divided by the time it took to do that displacement. And again, vector value, so that means your V average is a vector value. Okay, so we got our first real formula here. V average is displacement over time. Now, time, if we're talking vector scalars, is that a vector or a scalar? Time does not have you can't have time left and time right. So that's just a scalar value, so we don't have to worry about that as much. Now, delta x would be your x final, your change of position, right? So your position final minus your position initial. So you could write it like that as well. So these are all versions of the same formula. We're just describing it in different ways so that you can use it to solve different problems. But essentially it is average velocity equals your displacement over your time. Now, very important thing to talk about here is this is V average because it's over a period of time. So it is not a instantaneous velocity. It is not considered at any one point in time. It's your average velocity over 10 seconds or 10 minutes or 10 hours or 1 millisecond. Even if it's over 1 millisecond, is that still an average? And the answer is yeah. It's still over some period of time, so it's going to be an average. So that is helpful, but sometimes you want to know more than that. You want to know, I'm driving down the street, how fast am I going, or what is my velocity right now? Right before I hit that truck. Right before I have to hit my brakes. What is my velocity at that point in time? So we have more descriptors than just V average. So there are technically 3 different velocities that you're going to see often. So you have average velocity, which we just talked about, just your displacement over time. Then you're also going to see like something called an initial velocity. So this is the velocity at which the period of motion begins. So I'm driving down the highway at 65 miles per hour. I slam on the brakes and slow down to 20 miles per hour. So your initial velocity would be 65 miles per hour. And then when the problem is finishing up later, you're down to 20 miles per hour. So those 2 terms are not averages. They're considered instantaneous velocities. But you'll see those as well. So that'll be like in later units. Today, we're going to be focusing on this formula. V average equals delta x divided by delta t. So our first formula, we should try to solve some problems with it. So I'll put our formula up here just for reference. V average equals delta x divided by delta t. Okay. Whenever we do a problem, I'm going to have a set of guidelines I'm going to ask you to kind of follow. There's definitely a structure to solving problems. And the first thing you have to do is you have to gather your information. So when you're gathering your information, I'm going to be calling it listing your givens. So as we read this, we're going to be given some information. We want to take that information and list it out outside of the word problem so that we can better see it. So let's read it first and then I'll show you what I mean. During a foot race, Todd runs 625 meters due east in 85.5 seconds. What is Todd's average velocity? Okay, let's list the information that has been given to us in the problem. So 625 meters due east. What is that? So that is a displacement because it is a distance with a direction. So that's our displacement. So let's list our givens right here. I'm gonna have you do this for every problem, so get used to it. It helps solve problems repeatedly correct. It helps to solve problems in the same manner every time so that you get good at it. So your displacement, delta x, equals 625 meters east. Beautiful. That's our first given piece of information. What's our next given? 85.5 seconds. What is that? That is your time. So my delta t equals 85.5 seconds. And what else do we have? What is Todd's average velocity? So that's what we're looking for, right? V average. I often like to list it under my givens in this manner. So you know both what you have and what you're looking for. Now you want to go look for a formula that has all this information in it. Hopefully just this information in it. Now, we have one formula, and I just gave it to you, so this is going to be pretty standard, right? So the formula we are going to use is V average equals delta x over delta t. So let's take this given information, take our givens, and then plug that into that formula. So V average, we don't know, so that gets written as an unknown still. Delta x we do know, 625 meters east. And our delta t we know as well, 85.5 seconds. So now we just have to do that math. our V average equals, take out my calculator, don't know that off the top of my head, 625 divided by 85.5. So this is 7.31. I am rounding it for sig fig reasons, which we haven't talked about yet, but we'll talk about later. Now I need a unit. This is meters per second, so that comes with it. Meters per second. I need a direction, east. Not too bad, pretty simple. Problem solving. All right, let's step it up a notch here. We'll put our formula up here again. All right, during a marathon, we're looking for givens, all right? Whenever you start a problem, know that you're looking to list your givens. During a marathon, a runner passes mile marker 18 after 2.26 hours. Okay, that's more of a position than a displacement, but it's some information. And this is a point in time, but maybe not the time it took for the whole motion. So let's just keep going. The same runner passes mile marker 24 after 3.12 hours. What is the runner's average velocity in miles per hour over this period of the race? Okay, so here's the start of the race. Guy runs this way, and here is the finish. At one point in time, let's call this mile marker 18. It's been 2.26 hours. So our time here equals 2.26 hours. And then at a later point in time, he passes mile marker 24. And it is 3.12 hours. So we haven't done anything except kind of draw what we've seen, what it told us, right? This helps my brain make a little bit of sense of it. Now, is there an easy delta x or delta t out of this information? No, there's not. So we're going to have to use the larger version of the formula. So x final minus x initial. So position final minus position initial over time final minus time initial. Now, this will happen often in physics problem. You're going to signify one part of your problem or one part of the motion as the initial and one part of the motion as the final. So this is where our information started. So this is the initial time we are looking at the motion, and here's the final time we are looking at this motion. So that's our initial and final positions. So our x initial would be 18 miles, right? That's his initial position. His time initial is 2.26 hours. His position final is 24 miles. And his time final is 3.12 hours. And what are we looking for? We are looking for V average. Oops. Okay, we have successfully drawn the problem. We have listed our givens, and we've identified our formula, right? So the formula we are going to be using is V average equals x final minus x initial over time final minus time initial. Now we're going to plug that given information into this formula. So V average is still unknown, so we'll keep that as an unknown, V average. X final is 24 minus X initial, so minus X initial, which is 18. I'm going to leave my units out of it for now, just for clarity. My T final is 3.12 hours minus my T initial, 2.26 hours. All right, let's simplify this a bit. 24 minus 18 is 6. And that's going to be 6 miles, right? 3.12 minus 2.26 equals 0.86 hours. All right, essentially what we have just done here, this is our displacement. His displacement between the initial and final positions was positive 6 miles. He went 6 miles farther. And the time it took to do that, his change in time, was 0.86 hours. It took 0.86 hours to do that. So essentially this formula allowed us to get delta x and delta t. Beautiful. So now we can see that our V average is 6 divided by 0.86, which is 7.0 miles per hour. And I'm going to call that the positive direction. So that's pretty fast. I don't know that that's realistic, but I made up some numbers, so it doesn't really matter. So his average velocity over those 6 miles was 7 miles per hour. Beautiful. So we're going to practice this a bunch, but that is the formula and that is the general problem-solving technique that we're going to use throughout the entire year. So you'll see that over and over again as we go through, and we'll practice this a lot. Now, this is all word problems seeing velocity, correct? What if we saw velocity on a graph? So position versus time graphs, they are called that because the y-axis is your position and the x-axis is your time scale. These are often used to show velocity or motion of any kind, really. So these things called position versus time graphs are going to describe the motion of an object. And if we looked at car A and B, we could first say, did they end up in the same location? No. They started at the same location. Car B ended up 5 meters away. Car A ended up 10 meters away. Which car went faster? Well, car A went twice as far to a position twice as far away from 0 in the same amount of time. So that must mean car A had a higher velocity, and it does. Car B must have gone slower because it traveled only 5 meters, where car A traveled 10 meters and is in the same 5 seconds. So we're going to use these graphs to kind of describe motion and see what's happening to objects. So what we need to know if we're looking at a graph, so slope is rise over run, right? What is our rise in one of these position per time graphs? Our rise is essentially our change in position, correct? So our rise is going to be delta x. Our change in position is just our displacement. And then our run, your x-axis here is your run, correct? Your run is just your change in time, so delta t. So just by doing that, you can see that your slope is going to be your V average. Slope is rise over run, but in this situation, rise over run equals average velocity. So the slope of this line will tell you the average velocity of car A. So the rise, 10 meters, that's your displacement, right? Displacement would just be plus 10 meters. Your run, 5 seconds, that's your change in time. Plus 10 meters divided by 5 is positive 2 meters per second. So the only reason I added the positive here was to make it velocity. Because if you had a negative slope, you could just say you're going in the negative direction. And that would be fine too. So you can get velocity off of these just by calculating your slope of your line at that point in time. Okay, so if we're looking at this graph, let's try to figure out what's going on. So we start at 0, so let's go for a time scale, 0 through 10 seconds. At 0, it's at position 0. After 1 second, we've gone to 5 meters, 2 seconds, gone to 10 meters. So we have a positive slope here, right? So anytime you have a positive slope, that means you're going to have a positive velocity. And now, is that slope constant? Yes. So that means your velocity is constant. So we could find the slope of this line, which would just be 25 divided by 5, right? So this object is moving at 5 meters per second. 25 divided by 5 is 5 meters per second. Rise over run for this little triangle. And you could get the slope of that line. So that would equal positive 25 meters per second. Beautiful. Then it hits this second portion of motion. What happens here? Time's still going on, but this object is still at 25 meters, 25 meters, 25 meters. So this would just be called a constant position. The car was traveling along at some velocity and then stopped and sat there for the next 5 seconds. And we can tell all that just by looking at this graph. So if you have a horizontal line, that's going to be constant position. If you have a sloped line, you have constant velocity. What if you had a negative sloped line? Still would be constant velocity, right? There's a slope there. But that would just be in the negative direction. It started at whatever this is, 17.5, and went back to 0. So instead of driving the car one way, you drove it the other way. So constant velocity would be any sloped line. As long as the slope is constant, the velocity would be constant. What if your slope was changing? So here you have an object that the slope is changing. If your slope is changing, you're going to see this as part of our next section. That means you have a change in velocity. If you have a change in velocity over time, that's going to be called acceleration. So acceleration average, which you'll see next week, is your change in velocity over time. So if we look at the last slide, constant slope, you can calculate your velocity based on just the slope of that line. If your slope starts to change, that means you have a change in velocity, which we'll see is going to be acceleration. Now, what if we wanted to find the velocity at that point in time? Now, we certainly don't want to just connect the start and the ends and take a slope of that line, right? Because the slope of that line is not going to be your velocity there. That would be the average velocity for this whole 5 seconds. What if we want just the velocity at 4 seconds? Well, we can do that. So what we'll do is we will draw a line tangent to this line. This is terrible, but I'll do my best. If we draw a line tangent to the line at that point, and we're just to take the rise over run of this line, this tangent line, then we could calculate the slope of that tangent line, which would be the velocity at that particular point in time, instantaneous velocity. So beautiful. We got all these things we can get from these graphs. We got velocity, we can get average velocity, we can get instantaneous velocity. We can see whether the car is moving, accelerating, or standing still at a constant position, all by looking at these graphs. All right, so let's do a little bit of practice. Calculate the speed of car A. So speed, I'm going to change this to velocity, just to further start using that term. Okay, so car A, your V average is going to be your delta x over delta t. So it's going to be your rise over your run. So car A from 0 to 5 seconds, this is the rise. That was bad. Of car A. So that is 10 meters. And that's positive 10 meters, right? It went from 0 to 10, so we're going to call that positive 10 meters. How much time did it take? What is your run? This would be your run, right? Not getting better at drawing on the computer, by the way. Hopefully get better soon. So this would be your run. This is your rise. And this would be your run. So 0 to 5 seconds, so that's your delta t. So 10 divided by 5 seconds, we get a positive 2 meters per second. So that is the velocity of car A. Car B. What is your rise for car B? 0 to 5 meters, so plus 5 meters. What is your run? 0 to 5 seconds again. So your V average would be plus 1 meter per second. Beautiful. Just by looking at a graph, we can calculate average velocity very quickly, which is helpful. Okay. Now this is on you guys. So take out a scrap of paper or something to write with. And look at the following questions. I want you to identify which line shows constant position, which line shows positive velocity fast, which line shows positive velocity slow, which line shows negative velocity, and then I want you to draw in positive acceleration. What would that look like here? All right, hopefully I can figure out how to add a question, but let's go through it. Which one is constant position? Well, my constant position would be the line that the y-axis position never changed, because this is position, so if I have a constant position, it can't waver off of one value. So C would be constant position, because it just, as time passed, it just stayed in that one position. Beautiful. Then we have positive velocity fast. So we have two positive slopes. So it's going to be one of those two, because we need a positive slope and we need a steeper slope. Because we want fast, we want a higher slope value, so you want a steeper slope. It looks like B went a farther displacement in the same amount of time as D. So B would be my positive velocity fast. My positive velocity slow would be D, therefore. And my negative velocity would be the one with a negative slope. So this goes from whatever this value is, 20 meters, back to 0. So that's just going, its displacement is just in the negative direction. So your negative velocity would be line A. All right, beautiful. So now we're going to show positive acceleration. I'm sitting at this position. I sit there for a couple seconds. And then I want to speed up. Positive acceleration is speeding up, correct? So speeding up would mean that your slope gradually gets steeper. So this would be something like this. This would be positive acceleration. All right, what if I wanted negative acceleration? We'll do that a different day. I'm going to do that a different day because that will be confusing for you today. Later on, we'll do negative acceleration. Actually, I'll do it today. Why not? Say you're going quite fast. We have a steep slope. That means I have a high velocity. And negative acceleration would be slowing down, correct? So we need our slope to mellow out. So you need your slope to mellow out over time until here, and here would be a stop, right? If you consider that line to be horizontal. So right here would be negative acceleration. That would be going very fast and then slowing down to a stop. Call that negative acceleration. All right, beautiful. We will practice all these topics over your remote sessions, and then we'll practice them again when you come into class next. All right, see you.